Good afternoon. Thanks for making it here. It's actually, I'm sure a lot of people are waiting to go home, so I'm going to try not to be too boring. And I'm going to talk about deep learning, especially serving models with deep learning. How many of you actually have deployed deep learning models in production? Just heads up. How many of you have programmed the neural network? Cool. So I'm still going to have a couple of slides for those that don't necessarily know what we're talking about. In fact, deep learning is just a specific part of machine learning because we've been talking about AI, in fact, for 57 years. John McCarthy in 55 started to talk about AI. So today we talk more about deep learning, and deep learning is really a specificity of machine learning that tries to simulate the brain, and this is why we talk about neural network. And if you take the analogy of a neural network with human, for buying a house, for example, we work like this. We take inputs in our brain, like the city, the postal code, how many rooms we want in our house, or if there's a parking place, if there's some trees, all this kind of stuff, if there's a train around. And we make some second level kind of features like life quality, and then we bring different input together to create life quality, to do accessibility, or to talk about whether the house is friendly for our family. And when we have gathered all these facts, we make a decision on the price. Now, this is how the brain works, right? And in fact, it's really similar to how neural networks work in real. The only difference is for neural network and deep learning, we have the input, and then when we train, we give the output. And we train our neural networks, and what it does is removes everything in the middle and actually guesses, right? So neural networks, in fact, at scale, guess all the different features that will form the best possible output for different inputs. And that's why people are scared of neural network, because we don't know why they make their decisions, right? So there's no reason to be scared. In fact, neural networks are really friendly and they do a ton of stuff. And we talk about neural networks as well in terms of layers, right? So you saw in the previous slide we had neurons in the middle that were discovered by neural networks, and in fact we can have many layers, up to thousands if you wish, and this is why we call deep neural network, is because our networks are very many levels of hidden layers. Right, and we've talked about this actually for quite some time. Neural networks, I've been basically thought of for about 30 years, but there was just simply not enough computation or data to train at scale those neural networks, so we didn't talk about it that much. And really it's the advent of cloud computing and storage on demand, compute on demand, that make researchers being able to train neural network at scale. And that's why in the last 5 years, we've talked about neural network and AI again after 70 years. Right. So there's a couple of things to talk about deep learning, and especially why it's a big deal, because it's able to recognize cats, right? And there's so many cats on the internet, so it's very important. That's a joke, okay? Neural networks, especially in 2000, there's a particular type of network that was discovered called convolutional neural networks. And those networks, when I bet this is very hard to translate. You have to give credits, because I'm going to say some pretty weird terms. So those convolutional neural networks have been launched, and they've been extremely good at doing object classifications. And they've been so good, in fact, that now they are better than humans at recognizing objects. Right? We've, especially in the last few years, made enormous amount of progress, and now they are better than us and much faster. Right, so we use those deep neural networks, and especially convolutional neural networks, to do object detection. Can I have the time in front, because I'm like, yes, thanks. Otherwise, I'm going to go. So we use those CNNs for doing object detection, which is great, especially that now we want to do this kind of stuff a lot. These are a couple of GitHub projects where you can download those models. We do also face detections with those neural networks, especially convolutional neural networks. They're extremely good at recognizing features in the face. We do, of course, autonomous driving. Here, this is one of our customer called Too Simple, who is driving or use convolutional neural networks on live video feeds to train their truck to go driverless around the cities. And in fact, they've become so good with those neural networks that they are able to do it at night, which is pretty insane if you think about it. Of course, there's an enormous amount of data available to train those neural networks, so they are good at it. There's other companies that have started to work on new type of network. Here we're talking about what we call a prediction network, prednets, and those are able to guess what are going to be the next frames in a video. Or so given the first video, they will pretty much guess what's going to come. So this is really quite interesting because we are starting to predict the futures. There are other kind of networks which are pretty interesting, especially this is a new type of network that was published last year, end of last year, called CapsNet. And they do something nice. In fact, there's a big problem with convolutional neural networks. If you ask them to recognize face, and all of a sudden you take the nose, you put it here, the mouth here, the eyes here, he'll still think it's a face, right? Because it doesn't take the 3D position of those features or the visual, the spatial memory of those features. And now this is a network called the CapsNet that is able to do this. So basically they extract features and understand the spatial position of each feature and then are able to do classifications. Those are pretty awesome networks that are that have been used. And you see actually those networks are able to take the upper image and still recognize the same object with a different angle, right? So they have actually a 3D representation of that object and able to do that. Previous networks were absolutely not capable of doing this. Of course, there's been a session today about, or talk about LSTMs. These LSTMs are networks which have memories, so they take into consideration previous predictions. That makes them very, very good to do time series, right? And understand especially how to do text-to-speech conversion or prediction of the stock markets. This is also a GitHub project that is using an LSTM to do a German to English conversion if you are interested into doing that. And it's published on our lab, GitHub lab project. And this is the scary network. These are generative adversarial networks. Do you know those people? They seem familiar? Yes, kind of. Actually, they are fake people. They were created with data called the celebrity face data, and they are generated. So these are networks that are able to create humans, create things based on what they've been trained with. In fact, there are networks that are able to create real environment, given just few drawings of a house. They will put tiles on it, they will put windows, they will put car in the road, they will put trees around, simply because they would have learned that around houses, generally, there are stuff like this. So, a lot of different cool stuff, right? And of course, we use heavily deep learning at Amazon as well. We use deep learning pretty much on the entire Amazon.com website to do prediction and personalization. We've already had many customers talk about this. We've, of course, deployed also those deep learning algorithms in our fulfillment centers with robots, and they are specialized in doing collision avoidance because there's 50,000 of the robots in those fulfillment centers trying to deliver those parcels as fast as possible. We've deployed deep learning and models, and especially these are the LSTM networks, neural networks that are able to do text-to-voice conversions. Right? And of course, we also now started to experiment with drone delivery. Again, it's the same algorithm that are in autonomous driving cars to do collision avoidance and to deliver the last mile delivery for the parcels to our customers. That's always been a big problem. It's very easy to go Paris to New York, but the last few miles is very, very difficult. So we're starting to use drones to deliver parcels, or at least we are hoping we'll be able to do that. So, big question is cool, good luck. how do how do people use neural network, or especially how do we build them? I think that's a big question. Um, Luckily, there are some very, very smart data scientists, like many of you, and usually those data scientists and companies have been extremely nice, and they've basically trained and put those models online for you to download. This is where this comes, right? So we call those model zoos, and model zoos are basically repository where amazing people have trained state-of-the-art network and just put them out there. Now you might say, okay, but this is a network that is not really trained for my use case. Well, actually, you're wrong. There's a technique called transfer learning, which is a technique that takes a state-of-the-art model, and then you can tune with your own parameters to ask it to fine-tune your use case, right? So, for example, you can use a neural network that is trained on general-purpose data for images and tune it by simply tuning hyperparameters and then make it do exactly what you do. You just have to do a little bit more training, but you don't have to do it from scratch, which that is extremely difficult to do, okay? And it takes an enormous of time to do it from scratch. So when you start from a transfer learning and a model zoo, you, in a couple of days, can actually deploy models in production without you having to train it from scratch, especially without you having to collect the data, annotate the data, and do all that heavy 80% of the job, which is data collection, right? So the model zoos actually have been so successful that one of our customer, Expedia, has used that to do image classifications over the entire set of websites that they have. They've had hundreds of millions or tens of millions of images of different hotels. And you can imagine when people collect images of a hotel, they don't necessarily collect the best looking features. So what they've done is they've used a neural network to automatically select the best photos, the best looking photos, so that when you see that photo, you're most likely to click and book your hotel, because if you see a toilet, you're not gonna click that hotel, right? And they've done that by using a pre-trained convolutional neural network and just tuning the hyperparameters. So this is no black magic. In fact, they didn't have a huge amount of data scientists, and they didn't have to train the neural network from scratch. They used a pre-trained model. Transfer learning. So now the second thing, which was very difficult, is deploying neural networks, right? So traditionally, it's been very hard to deploy a neural network, and this is usually what you want to do. You want to have a neural network that does prediction, and you want to do this and expose this as a service so that your other service can call it and run predictions. But it's not easy. In fact, it's been very, very hard to do, and there are only very few companies that have done that, and mostly custom kind of stuff. So what we've done now, we worked on the system, and especially what we want to do is optimize model serving and make it very performant, very highly available, have capability to have an endpoint, an API in front of it, so that you can call it the same way you call any other of your HTTP service. You can, of course, out of the box, have heavy monitoring, because you want to be able to understand how fast your prediction is happening and all this kind of stuff. You might want to do A/B testing of different models, so you should be able to serve different models decoupled from each other and have those models have different type of metrics. And of course, you want to serve different type of frameworks. You might like, for example, TensorFlow, MXNet, PyTorch, or any other frameworks, right? And you might want to deploy your models on different type of platform, Intel or NVIDIA or this other kind of platform. So there are pretty much two types of model serving. One from TensorFlow, Google, that was published in 2016, which is a gRPC type of protocol to call your models, which is which serve only TensorFlow models. In fact, you cannot serve any other models out of it. And there is also a project research from Berkeley University called Clipper, which is a research project. So what we've done is we've worked with Facebook and Microsoft to create something called Model Server for MXNet. And this is actually a framework that allows you to have a REST and open API on top of your model. You can containerize your model, so you can, of course, test locally, and I'll make a quick demo. Test locally, and then push this into a Docker model if you want to push this into production. You have out-of-the-box operational metrics, so understanding how your model performs and all this kind of stuff. There is model archive out of the box, so all those the model zoos I've talked about, when you download, there's a bunch of different files, usually signature files. There is your network, there's the parameters and all this kind of stuff. And what we do, we have created an archive file that you can export into what we call a dot model file, which is actually something that you can serve, and I'll demo that as well. And of course, we also have now what is called ONX support, which is an integration of other frameworks. So you'll be able to serve TensorFlow, PyTorch, Caffe type of framework through that model server. Oof, 20 minutes. It's cool. I think I'm gonna make it. I usually do a 2 or 3 hours talk on those AI, so 25 minutes is a miracle. So how you do a model archive, you take your trained network, you have what we call the model signatures, which define what is the name of the model and the kind of characteristic of it. You have the custom nodes, which is actually the actual JSON representation of your neural network. And then you have all the auxiliary assets, and what we do, we created a CLI, a command line tool that takes this and exports into what we call a model archive. Then you have the REST API, which you can create from the signature. It takes the name of the network and automatically creates an endpoint, API endpoint, and then you can also automatically generate the description and documentation of your API from those files. There is default JSON encoding, so it fits pretty much in all of the kind of microservices and services that people are currently using. And you are able to do binary request payload so that you can upload images to do this kind of predictions, right, out of the box. Of course, it's an open API as well. Regarding operational metrics, those metrics support this kind of classic requests. What is the latency of your request? What are the resources that have been targeted? The dimensions of your models and the host name, of course, and then the targets, right? So everything which is where you want to send this information, whether you want to send that to a log file, a CSV, or through CloudWatch metrics, which is our cloud solution for logs. You can, of course, deploy your model first in your laptop just to test, but then in production you might want to push this into containers so that you're able to scale that. And for that there's kind of different solution. We out of the box support the Docker file, so we actually create the Docker file for you and then able to deploy your solution, which is based on Nginx with a Flask application behind Python Flask that is able to serve your model. ONX support is coming in actually a couple of weeks, and the first version of ONX support was pushed to Git a few weeks ago, so you can already start playing with it, and many frameworks will be supported out of the box. So I want to show a little demo out of it because I think that's the fun part. So this is the GitHub project where you can start downloading the stuff and play with it. And I want to particularly, if I found up here, so I'm the wrong here. So this is what you would download from a model zoo. As I said, you have a signature file. So a signature file looks like this: is that it tells you what are the input and the shape of the kind of your input, and then the output as well, right? And what kind of shape your data will have, and of course the input type. In that case, this network is a squeeze network, which is a convolutional neural network that takes an image as an input, and you can have a look at the SqueezeNet symbols there, so you can see how this look actually. So we have here, this is the whole file, and we have here our nodes, and those represent basically the different parameters of the neural network. And here you can see those is a convolutional neural network, and basically these are the kind of parameters of my neural network. Fascinating, huh? It's cool. There's, of course, the sunset, but that's the categorization of this is just the classic categorization on which we want to classify our image. This is a standard ImageNet SUNet classification. All right. So what we do when we do this, you can call MXNet model export, and here you can pass the model name. And here I will call this, I need to remember the syntax actually, sorry. It's always a problem. So model export, model name SN, and then the path where we are. And it takes this and create here, now you will see has created something called a model, right? So now my model is ready to be queried with an API to be exported. And what I can do then is actually call MXNet model server, and then use the models that I want to serve. And this, what it does, it will excellent. Okay, so let me remove too many files. This is live demo. It's cool stuff. Okay, this should work now. Oh. I'm creating there. So now I can save my my model, and here it's available on that. So you can see now I'll be able to serve that. Whoop, here. So I can call my model SquizNet here with different parameters, and you're wondering what is this kitten app? So this kitten, open kitten, is an image of a cat here, because that's what we want to play here. So really very fast, you download a model from a model zoo, you call export, create your model, .model file, and then you can already start to deploy your API and just have fun with it. Really, a couple of lines of code here. You can create a Docker image the same way, and same here, and then you can just launch it. Whoops. And here I'm doing the same thing. So very, very easy to start running it. All right, cool. On that note, I'm really impressed by you being able to cope with that. And thank you very much. Go and try it out because it's a pretty cool product, and contribute as well. It's cool. Thank you very much.
Thank you. Thank you, Adrian. Is there something that's really intrinsically different or more difficult about deploying deep learning models as opposed to other predictive modeling or serving other predictive modeling?
No, I think the problem is people try to tell you that it's magic and you shouldn't look at it and it's too difficult, but actually it's not, right? Everyone can just look at it. It's a couple of lines of code and it's just like, have fun with it.
Yeah. Is this system only used for serving? Or is it entirely connected to any software for training as well on AWS?
No, so that system is an extension of MXNet, which is our framework for doing deep learning. Yeah. And this is just to be able for you to serve your model very fast, right? So this is the project.
But it offers simple integration with the MXNet.
There are other services to be able to build models that you can use out of the box. But this is simply for serving your models. Yep. MXNet project. Open source, contribute. It's fun.
Thank you very much.
Cool. Thank you.